to control that, and then you can print with defect free or print solve harden later, for example. Next one would be not too long. If it's not too long, it's not many slides, but it's about show a kind of success case that we do using simulation. So this will be last two presentation for me. This will be the second last. There will be, first one is about more physics-based modeling, about multi-scale, multi-physics modeling. Another one is more combination of the data driven or machine learning based on alloy design combined with experiment to do about ABD series material, for example. And this is actually the work that we recently published in Nature Communication on the solute trapping that will show you some insight about what we have done and what is a way forward for the community on a systematic study on a system that we believe this will be important for the future in terms of the compositional defect or micro segregation. So as mentioned, this will based on this paper published last year, early this year. So on the topic is on the solute trapping. I'm not sure anyone here understands solute trapping. Are there anyone in the metallurgy field? Good. So what do you think about rapid solidification? What is an important aspect? And then why is solute trapping? Can anyone tell me a little bit more? Yeah, can you tell me what your understanding about this solute trapping or non-equilibrium microstructure and rapid solidification? Yeah. Right. If I get a more clear example, yes, please. Right. Oh, you mean phase transformation now is not melting, right? It's after. You mentioned it's after. Okay. And then. Yeah. Okay. Right. Right. Okay. Yeah, but it's not. That means it's not necessary. Is that necessary to happen only in additive manufacturing? It can happen in other cases. Okay. Yeah, we call bulk metric glass. Yeah, but anyway, that's all correct. Yeah. Another question. If you know solute trapping, can you comment on the eutectic formation during the alloy solidification? Okay. Sure. Thank you very much. So thank you very much for your engagement. So what you said is completely right, but what we are going to say here is solute trapping in our case is due to the rapid repeat thermal cycle in additive manufacturing that lead to something, as many of you said, non-equilibrium, non-uniform microstructure. And this is still unclear. How we try to understand this is to try to use the multi-scale, multi-physics model to give insight into this phenomenon, what happened, especially this one for nickel-based superalloy I think I didn't say much here, but and understanding of equilibrium nature of this intercellular solute segregation. So that means we try to resolve how this dislocation or cellular structure profile happen as well. So it's a bit scientific, and I hope you enjoy it some way, somehow. So what we are going to talk is give you a little bit background and motivation why we're interested in this work. And probably you may hear enough about nickel-based superalloy, because this is my research area for a number of years, that I'm talking a lot about this, and titanium as well. So what is a typical microstructure of AM? And we'll focus more particular on the solute trapping using a number of characterization technique, not only speculation. We need to observe something and then inform the model what to do. And then what is a heterogeneity that I show you a lot in the past lecture already. And how can we actually predict or do something about this heterogeneity? How can we homogenize this or not? Or what is a characteristic of this? And then method that we're going to look at is actually, basically the first item is CFD, is melting-based additive manufacturing. And then there is a solute trapping and elemental profile of the cellular structure. So the highlight here is cellular structure. How can we predict it? Actually, if it's happened in the melt-pool length scale. And what is the thermal mass solute transport during the deposition of the 4 nickel-based superalloy we'll show you later. And this, how this one induced the transport, this one induced to the structural evolution. Structural, in this case, in microstructure evolution during printing. I think, please bear with me if you're not in metallurgy field. So I'm trying to go as slow as possible, because we believe this one actually influenced the solute segregation here in superalloy, important factor for the crack susceptibility. So I will try to link this based on analysis that we done up here, and try to make some comment about how can we better design the new superalloy with better crack susceptibility, so avoidance. And then summary and conclude the work. So, I mean, just to remind you this slide again, that our argument is that we need new material for new process. That is the key message, because the existing superalloy or existing nickel-based superalloy are generally difficult to print, even 718. I will show you in the next slide why. And we usually try to refer to CM247 because this is a material introduced in 1928, which is optimized for directional solidification. Directional solidification used a lot in aerospace industry because they have a high volume fraction of gamma prime, 65% to a bit above, so 65% in nominal composition. 718 is actually older material, back in 1965, but this material is very superior in the sense that they use a lot in aerospace industry. No one can replace this yet. So in the state, trying to looking at pre-printing of 625, right, with a similar composition, but that is a study there. But this is a raw material. And then this is the tool we want to focus on. So you will see CM247, or we have another one which is directional certified as well, Inconel 939. But anyway, this 718 and 718 and 247 here has been used to print. But as I said, this is actually optimized for this raw hot working and directional certification. So do we need a new material that may be better for new process that we said, additive manufacturing? So we are now probably in the Renaissance period of additive now. It's become going quickly and probably going plateau in about next 10 years or so. Probably it's saturated at some time. So we need to rapidly find a way to produce this. I mean, and then we can move the technology forward. So in terms of alloy by design, this is not inclusive in the sense just illustrate the concept that we decide this because the alloy design basically to rank the composition that actually give the property that we want. That is the principle, right? You want to have whether or not precipitate strengthening. That means the particular element will contribute to that significantly. Or if you want to have chromium and aluminum, this is for mainly for oxidation resistant. Or if you want to have a long-term stability, is ruthenium will give you that. And if you, but the most important thing for superalloy is actually high temperature property in various strengthening mechanism that you have. If you talk about aluminum, titanium, tantalum, this is actually gamma prime forming element. And this will actually going to be gamma prime after or secondary phase. So nickel-based superalloy is a two-phase material, which is gamma and gamma prime. You can think of as a composite if you are working in composite area. And this gamma is actually softer phase than gamma prime. It's like kind of fiber, a carbon fiber composite. So we give strength to the material. But in this, the nature is quite surprised because I didn't have microstructure here, but just say verbally. These gamma prime, actually the way they form in the homogenized condition, they form in a cuboidal structure. It's so surprisingly due to the crystallographic orientation and some crystallographic relationship. I mean, this is in the L12 phase compared with the FCC. So FCC L12. So and this one is, if it's going to be the grain boundary strengthening, you may heard about using boron to decorate the grain boundary to keep the strengthening. So this is another grain boundary strengthening mechanism that we can induce to the material. Or if you talk about solid solution, it's actually refractory metal, including chromium as well. We give the refractory solid solution effect to the material. So this is how this is about 10-15 elements that we use for nickel-based superalloy. Combination of these, I mean, believe me or not, nickel-based superalloy is a multi-component alloy system from 10 to 15 elements. So that will give you super property like high temperature resistant and also a high temperature, degradation, mechanical, chemical degradation that resists to that high temperature mechanical and chemical degradation. So process by design. Previously, now we talk about composition. So I'm saying this as alloy. So there is nothing about process. Alloy is alloy. Composition is composition. But when you process it, it's probably different because when you process it, it's actually, for example, this is a very old work in 2000, 2001. They call numerical study by David Dye at Imperial now, but he worked his PhD at the University of Cambridge on the weldability of Inconel 718 superalloy. I believe if you are in Inconel 718 research, you will know this paper very well, that even you call this alloy is actually weldable or printable, but actually the working area or working or sweet spot is quite small. If you're talking about carbide liquation here, I mean not fully penetration, porosity formation, gain boundary, and then solidification cracking. This is a working condition only for this Inconel 718 with, under condition investigated here, definitely this is for welding. So they didn't do anything at that time. So they identified this defect and plot the diagram. And you will see that it's quite complex, even something we call printable material. So we have to notice that this is actually stannate cracking and stannate cracks susceptibility is used as a weldability indicator. So this is what is happened here. So based on the understanding of the gamma prime fraction, they believe that there's something related to gamma prime forming element, which is aluminum and titanium. And then they try to map this composition onto this they call weldability diagram, and believe that based on empirical study, I think that back in actually 1940 or something like that, there's a paper in US and try to identify, okay, this material is actually not printable, not weldable that time, and then this one is printable, but it's actually indicated by the green color here. This is actually weldable or printable material for nickel-based superalloy, existing nickel-based superalloy. So this is when you gamma prime increasing here, they believe, but I'm quite interested in this diagram because there's no gamma prime during 3D printing, right? In powder, have you observed gamma prime? No, but in this case, probably relevant, yes. But I don't know why people still keep citing this paper, because in welding, you have the parent material. Parent material is a fully homogenized structure when you weld it, right? And then that means in that material contains some gamma prime after homogenization. So gamma prime is relevant, but why? This is my speculation and also question. Why in AM people still referring to this diagram, even we don't have gamma prime at the starting condition? This is my first question, actually, when I was a lot younger than this, and this is inspired me to dig out more. Why there's no gamma prime? Why you link this? And this is purely based on empirical study on a particular set of material at that time. So again, there's some other people proposing this diagram again, but they later looking at more combination of gamma prime plus another phases, and then trying to say that, okay, again, this based on the experience, observation from experiment or whatsoever, and try to link that there is some ready weldable material in this zone, but again, not completely, because some zone is mixed up with the red and the blue dot here. So that's very weldable. Don't know what does it mean as well, and then difficult to weld. So or very difficult to print. Again, it's also linked to this forming element again. Again, if you say, that's why I carefully choose the word, this is a weldability. There is not AMability, because again, it's about the forming element, not gamma prime per se. That's his inspiration. That's why we believe we need the new way to understand this. So what we did, you can scan QR code here. That will bring you to the paper that's going to present here. But this is something elaborate more next lecture, because this is more about data driven as well. We screen ranking and then do a lot of calculation based on the existing nickel-based steroid database. And then what we did is actually we used the two indices here. I think I repeat it again. One is actually strain rate cracking Merlin indexes. Again, this is linked to the gamma prime fraction, but we add niobium and tantalum, which is small fraction, and then we say this is the indices. If you vary the content of aluminum by 0.01 weight percent, and then you will get the combination of the material. Let's say this one varies 0.01, and then another one 0.01, or keep it constant, vary 0.01. What you will get is that you will get about 10 million composition here in the range of the acceptable nickel-based superalloy, not too much. So because you have a range for each composition already for superalloy, and then you can get the, we call design space here, that you can looking at in the gray dot, and you identify the range that you believe this is a working condition for additive manufacturing, and then they kind of draw this line and get the window of the fishing range. As I said before, fishing range should not be 400 like CM247. I mean, this is also 350 as well. We set it below is about 300 or 280 something for both composition, and then we select these two as function of freezing range, and it's actually not too high in the cracking index. So one is actually very minimum in crack, I mean based on this index, and another one a little bit acceptable or at the border. So that's what we call ABD 850, which this material perform well at 850 degrees centigrade and 900 degrees centigrade. So we call ABD 900. And then we print this one out, and what we've seen previously that is actually minimum crack of crack-free in printing condition. And then you will see that the texture is not very heavily textured material as well. So we believe we need to looking more why this happened like that. I mean, it's combined. Now, we better understand based on this one. I mean, this is a 60, 50 years ago. They proposed. We better design this one using more knowledge-based methodology. Someone asked me what you use. You can look at some pattern that I will show a reference next lecture, last one, that you can find more information from that. Or the paper, the first paper in 2009, talking about number of empirical equation we use to feed in to the alloy design code, and also a thermodynamic calculation in the background. And yeah, this is what we got. And the question now is that why this is print better than this one? Why this one print better than the existing one under the condition investigated? This is the next inspiration. And this one, actually ABD 900, is not actually speculation that's print good, but we already, not me, but I mean the company, the spin-out company from University of Oxford, previously called Oxmed Technology or Alloy company, they actually successfully, commercialized this ABD 900 and use it in the rocket engine kind of print a thin wall structure using laser powder-based system. Has been tested. I think it's not actually new. It's quite old. It's 3-4 years ago. It's there. It's used. And after we published, just right after that at the same time. So why this working? Why it's not? The previous one doesn't work. What is the crack susceptibility? That is the motivation of the work here. So what we do, we said we try to use the computational framework to link this process, structure, and property relation, especially microstructure, and try to understand why it's happened like that. And then from the aspect of microsegregation, elemental profile, and solute trapping, we believe that may link to the crack susceptibility. That is what our hypothesis. And then what we do, we actually simulate this Melpool simulation of 3 nickel-based superalloy and try to link this to the property prediction later. So based on this, we talk about alloy design, we talk about process design. We want to actually design from microstructure design as well. So we link composition process to microstructure development. So the composition of the microstructure and control here has been very important in rapid heating solidification process, like I said before, because in this binary system, nickel titanium, you will see that it's not homogeneous. It's actually heterogeneous, solidification. You will see some distribution of the nickel and titanium separately, and that means there will be some grain which is formed inside the Melpool before surrounding with liquid, so equax may form something like that. So this is insight that we provide understanding from nickel titanium system here based on simple binary system. So it inspires us to look at this in nickel-based superalloy, which is multi-component system. Another impact on this microstructure design is actually about composition change induced by the process, because our previous work noticed that there is some change in the composition, especially the high vapor pressure element like chromium, and then even nickel itself also prone to vaporization as well. So the collaboration with Professor De Broglie and Dr. Mukherjee at in US, we can actually get some predictive capability of the composition change doing the 3D printing of these 4 nickel-based superalloy. I think that is relevant to the context in the previous slide that I mentioned. We will try to understand more why this one is actually not non-printable. So at Queen Mary University of London, in my research group, we are having the 3 frameworks. So we do melt-pool simulation, as I said, in what you've seen yesterday as well in the lab session. And then we do solidification, liquid-solid transition here. And probably you can implement some solid-solid transformation framework here to understand the phase formation. Again, this is subject to the rapid solidification. I will give you some example of 2 material systems before we go into the main content of superalloy. The first one is titanium 6-4. So this is one of the important material that you use for implant application as well. So you will see that even this is the tertiary system, Ti-6-4, is still complicated enough that if you follow this dashed line, when you become liquid here, it's liquid here, and then if you cool down the temperature up to solidus temperature, 933 Kelvin, and you trap into this, liquid beta grain zone. It's a bit mushy zone before you reach to the solidus temperature at 1978. And this is the beta grain, which is BCC in nature form. And once you reach to this about 1269 Kelvin, the beta transformation temperature is transformed from beta to martensite, and then after that go to left martensitic structure. So how this actually transform is important, because in titanium 6-4, the spacing of the lathe is so important for the final property. So we want to see how can we predict it under the condition of 3D printing. And this is what we introduced the framework. The paper just published very recently, not I think 1 month or less than a month ago. But what we do, we first predict the ply beta grain. So what we see is a ply beta grain, and then after that you need to impose the phase transformation from here. Just this boy is so complicated to transform it to be alpha and articular phases, martensite here, and you can get an idea how this microstructure evolution. And this is actually happened in real life. We simplify this diagram to be about it. So you will see that this is, if you're interested in this, if you do some kind of diffusion-driven problem, this if it's followed as normal, it will be like this in forging of the titanium 6-4. But if it's rapidly cooled, the phase which is formed will be alpha plus alpha prime. So it is so complicated now, because the martensite here is so important. How can we understand is how it's formed, and how can we avoid that? And what we do a 3-layer deposition under the direct energy deposition process. And we try to get ply beta grain, first of all, and then we predicted the transformation at different locations of the build here. And then you will see, you can get some feature. It's very fine calculation here under collaboration with Beijing University of Technology. So compare with TM with the triangle, that you can see the feature the same in the simulation. So basically what we compare is actually we compare the whole figure from experiment and the simulation. This is what this kind of simulation can provide you. And we believe this model can be beneficial for changing the process condition later. That is the idea. But the framework here is a mathematical framework, quite complicated, that you need to link with a computational approach. This is an example that want to show that why this so important. And then if we can understand that, we may be able to understand how can we reduce a crack susceptibility as well. Again, but titanium is so complex. I'm not saying nickel is easier, but what I want to make just bring your attention is that different material system, if you come to ask me, you're talking about aluminum, copper, nickel-based superalloy, I would need to ask you which nickel-based superalloy you're talking about. It's going to be gamma prime or gamma double prime delta, or it's so many variety of nickel-based superalloy in the metallurgy point of view that will make it differently in terms of solid mechanics. Or if it's solid solution nickel-based superalloy, is also another story. So it's, as you know, from mechanical engineering. But nickel-based superalloy, that what we're talking about, is mostly gamma prime strengthening superalloy. So our inspiration to do the simulation in the microstructure detail in nickel-based superalloy, because as you see in the build along build direction and transfer direction, it has different microstructure clearly from columnar grains to equax grain, and this is with the cellular structure. Along the build direction, you may get this kind of melt pool and feature at the time scale and as its length scale. And the cellular dendritic structure here is a micro to nano, in the micro nano scale here, induced by ultra high heating and cooling during LPBF. And the in-situ observation of this phenomenon, especially solute transport and microstructural evolution, is very limited. I think I would say almost none or no such observation, because the resolution of this is quite small. And the high fidelity simulation will be relevant to rationalize this, what happened in terms of later matter interaction, heat mass transport, and subgrain scale we're talking about in the 10⁻⁶ to minus a micro or about 100 nanometer scale. This solute partitioning between cellular or dendritic trunk and intercellular or interdendritic region will contribute to the non-equilibrium rapidification nature. So we'll be study this solute trapping or solute transport in subgain scale and try to understand the non-equilibrium during or after rapidification. So what we do, we suspect that why the new design superalloy is crack free. So we try to observe using first X-ray synchrotron image diffraction in light source at Harwell in Oxford, and combination with atom probe tomography in as printed condition, combined with the high resolution scanning electron microscope or STEM. And then we do the secondary iron mass spectroscopy to understand the oxide at the aspirated condition for these two alloys. And then you will see that there is no gamma prime peak present detected by high energy light source like synchrotron at all. And its print solid solution, actually you will see here, it's a perfect solid solution material after printing. And atom probe also shows some, there is some segregation, but it's not actually heavy segregation. If we do it at different, if we do post-treatment and at different, sub-solvers or super-solvers, you can actually segregate out or homogenize out some structure. And then this is quite solid solution. If you see profile here, yeah, there's something across the boundary a little bit. But this is what we got, and then we know that, okay, this different from existing alloy. So now, what happened to the crack sample? What happened to the crack sample? The crack sample, actually, we identified this crack propagation that we said due to the ductility dip here. And you will see that there is a zone that trapped, and probably they changed the microstructure a little bit from columnar to kind of equax. And then this is a black, dark shade light zone. And then we try to make a kind of hypothesis what happened here, why it's actually stopped here, rather than penetrate through this crack. And this is another curiosity that we do. And then we know that the crack greatly accelerates the rupture of superalloy in high temperature condition. And this segregation basically determines the liquid film formed during solidification the solute segregation and liquation in a heat affected zone. Something that remain unknown is that how these solute transport elements are transferred during non-equilibrium rapid and repeat thermal cycle. And because we don't know why it's actually trapped at the bottom of the melt pool. This is the question we ask ourselves, and then insight into this transport will be actually provide a better understanding what actually hopefully going to eliminate crack defect, because if we know this has an impact on the crack propagation, we can do something to mitigate that. And then that's what we are trying to do too. We believe this will be a key understanding of solute transport here will be key for the additive manufacturing processability. So what we do first, we ran a model to understand. This is the real simulation in 718. So we will tell you later that I will tell you later that we calibrate against the small scale, I mean how to say micro or nano length scale experiment as well. So we calibrate this before we predict the solute segregation profile. Especially for in class 718, we chose niobium segregation profile because this is a detrimental phase that's present. So what we do, I think I don't need to repeat this, is in the very first slide. And then you will see that we can predict niobium distribution in the Inconel 718 here. And it's actually real that it's happened at the boundary. But we not quite understand yet. This is just quite a big level, big scale model. Next thing we want to do, we try to solve this big equation here and incorporating the solute transport as well in the multi-component system. So that means at the different nickel-based superalloy, you do a pairwise calculation for each system coupled with thermodynamic data available that you can actually extract the solute concentration, these partition coefficients that I will talk a little bit more about K later, linked with the process condition like platelet number like later. And then you use this understanding to develop understanding how the microstructure evolved. And this solute concentration is actually in the range of the concentration here, partition to C naught to C naught divided by by K here. And then this is the, we call segregation indexes. So if this one, if it's less than 0, will fall into this one. If more than this, it's fall into this one. And then we identify the segregation profile specifically for CM247 based on our understanding in the experiment is a hafnium at the segregated in the grain boundary, and the niobium for the lava space, which is decorated at the grain boundary as well. So we focus on these two, but there is some other reason why we focus on these two profiles from metallurgy point of view later. And then interestingly, because the new superalloy actually solid solution, so we use the avalanche segregation index for the new superalloy. So that is equivalent, or what is it called, equivalent segregation index. So it's an avalanche profile. So what happened, we will see now. So the reason why we chose these three, because this is a composition studied here. So we have hard to print, gamma prime strengthening hard to print alloy. Yeah, we have Inconel 718. Supposed to be easy to print, but this is gamma double prime strengthening alloy. We have intermediate gamma prime strengthening alloy designed for AM here, which is a new composition. This is the three material that we are studying here. And then you focusing on this one, hafnium. It has only 1.3% weight percent, but instead of niobium, it's 5% here. And this is what we found. And then this is a verification of model using 718. What we did, we define a calculation domain here, identify between the multi-phase solver. So that's what you've seen before, nothing fancy. But what we got here is actually dendritic. If you remember yesterday, Hong Hao present, this is what we can predict. But this is it's a 3D, but a thin slab of 3D represented by the fluid flow in the 3D model. And then you see, this is prediction, not experiment. The predicted structure here, in terms of dendrite arm spacing, is so similar to the male pool in the experiment. And when we look closer to this is a primary dendrite, you will see this is the spacing of that is in the 1 micron scale. And we use this one to validate against the wavelength dispersive spectrometer in the electron probe microanalyzer APMA here. And you want to validate or verify your model with this segregation profile across this one, and then experimental and simulation. So to make sure that your model is actually predictive enough to do something further. And this is only extract only niobium profile. And after that, you're looking at different location of the male pool and try to extract some average dendrite arm spacing at different level, because this is the spacing that segregation profile taking place. So a summary of this is niobium concentration distribution is across the cellular structure, cellular trunk here, and intercellular area. I mean, that's why I said micro segregation linked to the dislocation. That is the next study actually. So segregation length here is an oscillation of the solute profile is increase and decrease because of refinement of the cell structure during the high solidification. And this simulation result has been verified with experiment in terms of the solute trapping. So we can approximately capture the effect. And what we do now, we try to use this for a particular cases. So this is what happened in a multi-track, multi-layer deposition. So we start with the average segregation profile. You will see this is some layer adding up. And then what you see here is about, this is a thermosoluto fluid flow that actually doing rapid solidification of 2-layer deposition here. And I want to highlight here in the average composition here that the solute actually enrich here once the second laser attached. In the first layer, you leave behind enriched solute zone and the solute dilute zone. And this actually, as for solidification progress, the cellular structure actually taking place. This is a panna growth because we're talking about high cooling rate, right? Panna and cellular structure will form. And after that, once this one progress, the solute enriched zone actually going up and is leave behind the solute dilute zone. And after that, the cross structure, due to the fluid flow as well, it will give this cross structure. And you get the severe segregation profile here. After that, once another heat actually put it in, before this is the first track, right? First track. The second one, there in overlap zone, the heat input here will push away this solute because it will be remelted again. And then this zone has been remelted. And then this is sufficient solute mixing. It's mixed together. And then this leave behind the solute dilute, so there is no heavy segregation at this one. So the panna growth actually proceeding to grow this way. And the cellular structure actually become penetrated here. This make this one enriched. So you will see that enrichment of the solute actually related to cellular growth here. And then you get that this is improved solute distribution. That means if you print it more and more, the solute will, but still, some cases, without care, you will trap some solute, and that's what we call solute trapping. What we see, what does it mean by that? If you see here, this is male pool, you see with the porosity as well. In CM247, if we move a little bit to the highly segregated kind of material like CM247, we talk about hafnium profile. Again, this is coming from modeling only. So you will see this is substrate layer and then second layer here. And then the metal here is actually, this is a male pool, heat affected zone, solidification progress here, and this is still in liquid here. So you can identify based on the gamma prime forming element. Again, this is not gamma prime yet. It's just a forming element. There are preferential segregation of some element based on the calculation here, that in the isotherm of the solidus temperature of this melt pool, you will see that there will be some in the liquid and in the solid. That's what we call dilute or enrich. It's based on quantitative measurement here. So previous slide, that's what we do. So we will see that in the liquid, this actually dilute or otherwise enriched zone. So that's one. We cooperate because we believe this is in the eutectic zone here, nominal composition here, but you actually trap into the rapid solidification zone that actually move a little bit that MSE and MSL here to be closer. So that's why I mean this is something doing with this phase diagram systematically, and then you will see the strong inhomogeneity of the process here lead to the what we call quasi-solute trapping. So when you get strong inhomogeneity here, in the second layer, that will trap a zone like this. I think if you go back to your sample, I bet that you will see this kind of thing as well. Most of the time, that's what we'll observe across the sample. It's not things speculation, but I think there's something doing with the process. So that's why. So we try to relate now. So now, what is the use of this? At the end of the day, I ask myself, what is the use of this one? Actually, when we know hafnium profile here, you'll see some highly segregated profile compared with the 718, which is actually quite good segregation profile, but still you have some segregation. But whereas these, sorry, I mean, this is CM247 is highly segregated. You will see a lot of hafnium present everywhere, consistent with what we've seen in the experiment. And then in concern is kind of intermediate, but this one is not really segregated a lot, but it's quite of average. So that's why you see this kind of zone acts as well. This is a zone that you see, which is we call solute dilute zone, right? It's trapped in the melt pool, and this is due to because we believe effect of the melt convection during the printing make it actually. Let's say if you decrease the cooling rate here, let's say this is the solid liquid interface. And once the convection, if you have the convection flow, this will actually, it will actually increase this zone. So convection will suppress this, but so strong flow will going up here. And this solute trapping induced suppression will be impact on the niobium concentration. It will be from strong to suppress this zone, and that's actually the promotion of this convection actually give rise to the increase in the I think increase to the undercooling temperature of the crystal growth. So if there's sufficient convection, it will increase the undercooling, and the partition coefficient, which is K, will be increasing. So this gap here will lead to difference in the partition coefficient during processing. And that is what it is here, the variation of partition coefficient when you have, this is partition coefficient K, and then this is the platelet number, which is linked between the crystal growth of the process. There is a interfacial velocity of the growth, interfacial width, and the solute diffusivity in liquid. And then if you use this as an index, you will see that means if you have the larger platelet number, that means you probably promote more interfacial velocity. The melt pool is travel faster. So that means if you quickly, bang a lot of energy into your system, you will fall into something called solute trapping zone. That means it's not equilibrium anymore. It's going to non-equilibrium. And this is actually the blue one related to your, this is not your scan velocity, no. This is due to the scan velocity or energy is contribute to the velocity in the liquid. And this diffusivity here will promote this zone. So you get trapped in this zone. Or it is a freezing length coefficient, because if you have very rapid solidification, this one will actually promote or change your freezing length as well under printing. So it changes based upon this equation. So your moving interface or liquid here, it will change based on your partition coefficient here. And that actually, the magnitude of this identify something we call characteristic solute trapping velocity. And if this solute or interfacial velocity actually very high, in the range here, 0.1 to 1 here, intercellular segregation will taking place, especially the partition coefficient such as hafnium and carbon that's far from 1. So that means it will trap into this zone. And then if you're talking about in near equilibrium one, if your high solidification rate as well, if you are in this zone, it's still trapping as well. Your freezing length will change. So it will be decreasing. So such as the solute profile that contribute to this, as I have zirconium and copper. So what is mean here is that the process parameter is so important that we know in CM247 LC. If you change your hash spacing, power, energy, you will actually get to different crack density based on the previous study here in the LPBF. You will see if you use lower density, your linear energy density even higher, but your crack occurrence is actually lower. But in the case of CM486 here, it just shows similar composition here. And this one contribute to the energy density that contribute to the interfacial velocity that talked previously. But that means this is suggestion now. The influence of the common element in superalloy on crack susceptibility. I mean, this can be found in the Nature Comp paper if you like online. So the freezing length here will be varied as well based on the process parameter you use. Surprisingly, that means we cannot control like casting. We know the freezing length, so dynamic, the process. Second, segregation length. If you see in the yellow exclamation mark dot here, that means the composition that we need to take care of a little bit more in terms of solute trapping, because hafnium, zirconium, and copper actually contribute to the crack susceptibility as well. The graph to solute trapping here, so this one is okay. Freezing length, hafnium also contribute to segregation length and also freezing length as well. So this is the new crack susceptibility that we identify based on the insight from the model. We believe that in the alloy design of superalloy, new superalloy, if they have different solidification behavior of superalloy, will be easier to reach the solute trapping if strongly partitioned solute element were removed. So that means if we can remove all this, but probably it's not good for this hafnium because this is a grain boundary strengthening element. Not sure. Or people trying to see the role of carbon as well. And the larger segregation range mean the wider gap of solute trapping you will get. That means hafnium you have a lot in the CM247. This will be detrimental to the crack susceptibility. Sometimes, I mean, it would be more challenging to reduce and complete elimination crack, but it's about control and optimize process parameter as shown before that may help, but not a lot. It's about what is the acceptable range of the crack, but probably we may not we cannot compromise with crack, right? In a flying component, it's probably not possible. But this kind of insight, I mean, you see now, I'm really trying to link process with composition, with microstructure, and now trying to say about property. So this all the, I mean, PSP is a way, the motto for our research, that we try to show that this model can give extra information. It's really extra more information that you can get. And this is the, I mean, these two, apart from freezing range, we add one more from the previous design alloy. We add segregation range as well. So if you map this across, representative nickel-based superalloy, based on the understanding that we said previously on the lower length scale model, we can see that the green one represents something that the range that we can print, but the cross dot here is, I mean, this is a processing window, and this is the cross here is indicate the not hard to print alloy. You will see that most of the time they have very high grain boundary segregation, a strengthening element and primary element for gamma prime. This is systematic investigation now, but it's not all the time that you have some percentage of gamma prime and you cannot print them. You see that means what is said here is mean that not only one parameter can say to you. It's sometimes controversial because some high gamma prime, some of them can be printable, or processing window is wider. So high gamma prime like CM247 or incandescent 308 LC is considered unprintable with crack, but even higher like Raynaud 77 is crack free based on the literature. Definitely, it's probably not the same condition, but this is what we found. It's a bit controversial as well, but I mean, that's one of the things that we make an argument in the paper. And higher hafnium plus zirconium here will be hard to print, and this related as well with the high gamma prime phases, nickel-based superalloy. So elemental segregation worsen the printability of precipitate hardening superalloy, and as well, this will sensitive to the cyclic thermal stress. And the crack may be eliminated in the hafnium-free CM247. Again, this is, we made some suggestion. Whether if we totally remove hafnium, we can print it better. I think you may know some study talking about the variation of hafnium in the CM247 as well. So we believe high gamma prime nickel-based super with less grain boundary strengthening element will be the ideal solution. So the suggestion is that strong tendency of solute segregation in cellular trunk and intercellular region will further impact the solidus temperature. So as we said before, the freezing range is changed, and changes will change the solidus temperature as well. So elements such hafnium and zirconium are strongly recommended to avoid. So we want to remove if possible. Whether or not it's possible is another question. So in kind of summaries, I just want to say that the fully coupled thermofluid soluto microstructural mathematical model is developed to understand dynamic solute transport and element segregation in AM. So we reviewed that the non-equilibrium nature of intercellular solute segregation and cellular structure here occur at the sub-grain scale in the multi-track, multi-layer fusion and certification of LPBF. And the prediction of the melt-pool solute trapping zone microstructure are verified by the reported available conducted experiment. So we have used both literature and also new set of experiment. The role of this melt convection on the elemental segregation is proposed as a mechanism to form the solute trapping region and microstructural evolution. Hard to print superalloy can be additively manufactured without removing essential a minor element by further accelerated the solidification to promote the solute trapping and hence reduce intercellular solute segregation. Qualitative estimate of the crack susceptibility in terms of the processing window is developed. I think I showed you before. And I hope this will aid the alloy design of superalloy for the future. So we hope this modeling framework can be powerful too. So this modeling framework we're talking about is more multi-physics, multi-scale simulation here. Will be useful for further develop other study like this one will be useful when you want to do or design a new alloy in additive, especially in the case of blend elemental powder. So we call in situ alloying. You alloy A and B, it will be AB or ABC with AB, which a lot of study, especially in the high entropy alloy community. They mix 4 or 5 together and blend it under the beam. So this is probably a way forward and keep more opportunity rather than going to do atomization all the time. But anyway, this is some kind of further work, and hopefully this can be beneficial for elemental powder in high entropy or performance steel as well, which you have less number of elements present in your process. But again, this is just outlook from this work. And I hope this one is a showcase for multi-scale, multi-physics to really bring bridge the scale from low length scale to the impact on the industrial scale usage for alloy design. Again, this kind of understanding will be fed into the alloy design algorithm for data-driven, for example, and that will be the last lecture tomorrow. Thank you very much. And are there any questions, please? Yes, sure.
In one of your slides, you have shown the new alloy that you made based on merit of strain edge cracking.
Based on?
Merit of that SAC. That strain edge cracking index.
Yes, strain edge cracking.
Yes, sir. Can you go
but
to that?
That is the early inspiration of this work.
Yes, sir. So
you ask something about tomorrow again. Okay. I know what this one. Yeah.
So this is the previous one.
Previous one.
Means where the micrographs are showing reduced cracks. No cracks in the new alloy, cracking in Inconel 718.
I think that's
here.
Yes, one?
Yes, sir, here.
Okay.
So the micrographs are showing hot cracking and the intrinsic strain edge cracking.
No, be careful. I already said it's so many cracks actually acting on this. You can see more in this ACTA paper how many crack mechanisms operated. But what is your question?
So in the micrographs, they are solidification cracking. In the micrographs,
mixture, no. It will be ductility dip, liquation, lack of fusion. I mean, the crack here, it's hard to identify because based on imaging, we will say the crack in this sense means any line in the microstructure. We not classify yet because the one here is image-based analysis. It's not like tomography that we can identify the feature like the previous work. That makes sense. This is just about MSc, PhD. I mean, this is the same one I showed you previous talk, but this is just inspiration. So okay. I just want you to be careful that this is just a way to quantify the defect content in the printing, but we call this crack susceptibility. We call all these are crack. But this feature, including this may be liquation, solidification, including something of porosity as well, because it will, once we do the different contrast in the image, this will bring up. We will not remove any feature. But that means you need to have a criteria to remove it, but not yet. We didn't implement anything because how can we make sure we select the right? But this defect in this vicinity will be captured and then analyzed. So what you may say is actually, if you remember my talk last one, you will see the distribution. The smallest part probably related to some defect. The bigger side with the lengthy one may be cracked. I don't know, but this is something we need to do further analysis. Does this make sense?
But those cracks will not be SAC cracks because they are as fabricated. Those samples are as fabricated. There cannot be strain edge cracks. Correct, sir? Because
you're right, but if your print is quite high, at below you have intrinsic heat treatment.
But no gamma prime was reported. You are saying that in...
yes, but that is why I mentioned that this has to be improved into the alloy design. Because this is not, they make assumption the same as they have gamma prime. But actually no. But this is the best assumption at that time back in 15, 16, that they first done. So this understanding that I show you later is not yet available. So you need to consider the timeline as well. So this is a huge amount of data and effort to make it. Because this one based on the alloy design in the disc and turbine blade. Yeah. I know what you mean, but that's why I said no gamma prime why you matter here. But anyway, this is the best approximation that time. Model just a representation of reality. We cannot expect 100% accuracy, but we need to use with caution. We need to know the condition, what is working. Yeah, I think. Thank you. Any other question?
Sir, I have one more question. Like, let's say I print a big turbine blade. Let's say a big turbine blade. From top to bottom, the segregation profile will vary. Let's say in top there will be more segregation, in bottom there can be less segregation.
I think another way around, but anyway.
Sir. So the question is like how to go about the heat treatment procedure, because how to ensure that part throughout is homogenized, precipitation, volume fraction is uniform from top to bottom. Since we have
I think there's so many things to do. It's not about heat treatment only. It's about the way you fabricate it as well. Because you cannot expect something highly segregated at the bottom, and then you will homogenize throughout, the probably 30, 50 millimeter up. But later, I think, in my opinion, you need to change your printing strategy, like scanning pattern, try to control different way to get better thermal signal that can homogenize the structure as printed. That's why digital twin may come to a big play in this kind of research. So that's why we need to collect it on time, on fly, yeah. So it doesn't mean after only. It has to be during as well, yeah. Because if you have heterogeneity across the sample, it's probably an easy fix for heat treatment. But if it's highly concentrated, I don't know. The best way is just remove the base. I don't know, yeah. But again, I'm not in that length scale yet. There's my previous postdoc now, academic, he's looking at heat treatment. There will be some interesting heat treatment as well as a following paper for the successful material here that we published in Superalloy, that you can see different heat treatment protocol lead to different microstructure, and hence we identify the liquidization effect during this, as a result of this structure. And you can follow, it's actually in 2020, this paper, yeah. But I don't think you can homogenize, but I may be wrong. There may be another way. Yeah, thank you. Any other question? You want to ask?